Assalamualaikum and hi everyone. So we are from Group 21 and we would like to present to you about integrated design project focusing on separation process 2 and reaction engineering 1. So this is our members. The first one is me myself Amirul Irfan Haziq bin Muhammad Suhaimi. The second one is Ahmad Adib Syahmi bin Badrul Hisham. The third one is Muhammad Haikal Shazwan bin Suliman Shah. The fourth one is Alia Najihah binti Mat Jalani. And the last one is Asma Inaku. So, let's move to the introduction part for both subject, reaction engineering 1 and separation process 2. So, let's go to the reaction part. So, basically, in this project, the reaction part is focusing on the key chemical in industry, which is methanol production that are most commonly used in industry. This route is from the syngas route, that synthesis from carbon dioxide, carbon monoxide and hydrogen gas. This produced from steam methane reforming. So in this part, the catalysts that been used in this reaction are copper, aluminium oxide and zinc oxide, and the reactor used is plug flow reactor. And the main reaction occur in this reaction is the production of methanol by using carbon monoxide and hydrogen gas. So the main reference for our production is 1 million ton per year that are produced in Sarawak Pet Chemical Plant in Bintulu. So the second one is introduction for separation process. This is proposed an absorption-based purification system as an alternative for distillation column. So this absorption-based is basically has advantage including lower energy consumption relative to distillation and suitable for removing trace impurity to achieve high purity specification and operational simplicity. So let's move on to the second part. So this is the objective part for this project. We split the objective into two parts, which is reaction part and separation part. So the reaction part is basically focusing on the syngas route over alternative route based on technology maturity, feedstock availability, energy efficiency and industrial relevance that basically focus to produce methanol and to write and explain about main and side reaction. But for the separation process, it is most likely focusing on the absorber itself, about how it worked to achieve the 99.5% of purity, to estimate the required absorbent quantity for continuous absorption system, and describe suitable regeneration under the absorbent. So process flow diagram part begin with the two stream, which is methane and steam stream, entering the mixer and go to the heater to increase the temperature, and it will go to the compressor to increase the pressure and suddenly enter the reactor to undergo two reaction process to produce carbon monoxide, carbon dioxide and hydrogen. So it will go through the first cooler before entering the PFR. At PFR, the three reaction will occur, but the main reaction will only focusing on producing the methanol. And after exit the PFR or plug flow reactor, it will enter to the compressor to increase the pressure, to decrease the pressure, and entering the second cooler that will undergo to the separator. And the last one, it will go to the absorber that will focusing on separating the water and the methanol to achieve the high purity, which is 99.5% of methanol.
Now we move on to stoichiometry table and material balance. We will discuss about the first part, which is stoichiometry table. We only use the main reaction, which is CO plus H2 equals, we will get methanol. And we consider all of this as an elementary reaction. For CO, the initial would be FA naught, change negative FA naught X, remaining in terms of flow rate, FA equal to FA naught in bracket 1 minus X. H2, the initial would be FB equal FB naught, equal to FA naught. Change will be negative to FA naught x, and the remaining will be FB equal to FA naught in bracket 2 minus 2x. For methanol, there is no initial. The change will be FA naught x, and the remaining is FC equal to FA naught x. So we consider the expansion factor because temperature in and pressure in is not equal to temperature out and pressure out. So how do we find the remaining in terms of concentration? First, we find the epsilon, which is 0.14 in bracket 1 minus 2 minus 1, and we get negative 0.2x. Now, we expand the formula FA equal to FA naught in bracket 1 minus x, and we will get CA equal to CA naught in bracket 1 minus x over in bracket 1 plus epsilon x times with T naught over T times with P over P naught. And we just apply all the formula to get CB and CC, which is like you can see from the table. Now, for the second part, material balance for the reaction. So, from the table, we extract the value from the symmetry. Now, we will calculate the conversion. We use the formula FA equal to FA naught in bracket 1 minus S, and after the calculation, we get the conversion 0.5, which is 85%. Now, we use back the formula that we from the stoichiometry table, which is the remaining in terms of concentration, to find the concentration of A. As you can see, after we have substitute all of the value, we get the concentration of A is 0.0326. Now, we will calculate the error. We will use the concentration that we get from the formula and the concentration from the symmetry, which is in bracket 0.033 minus 0.0326 over 0.033 times 100. Then we get the percentage error is 1.21%. Now, for the CB and CC part, we also use the same formula that we get from the stoichiometric table, which is CB is 0.2596, CC is 0.1847, and we calculate the percentage error for both of this, and we get the percentage error for CB is 34.31% and CC is 36.66%, which is quite relevant and normal in the industry.
So next we need to determine the type of the reactor and the catalyst. So our reactor actually managed to get 85% conversion. So I construct a graph of Levenmuir, which this data actually comes from the symmetry itself. So Levenmuir is very important to determine the volume for both CSTR and VFR. So to calculate CSTR, we use the formula of V equal to FA naught X over negative RA. So for X equal to 0.85, the FA naught over negative RA value is 51.76. So substitute the value and we got 44 meter cube volume of CSTR. So for VFR, we use the formula V equal to FA naught times with the integral of 1 over negative RA dx. So I use the Simpson rule, which utilize 5 points, as you can see at the slide, where the points of X and the value of FA naught over negative RA for each points. So I substitute the value and we got the volume for VFR is 26.63 meter cube. So based on the calculation, we choose VFR over CSTR because it requires a smaller volume for the same conversions. This is due to VFR that has higher reaction rate at the inlet, which will be utilized around the reactor length. In contrast, the CSTR actually has lower reaction rate because it follows reaction rate from the exit conditions. So that's why CSTR has higher volumes than VFR. So as the methanol synthesis actually favors decreasing reaction rate with conversions, so that's why we choose VFR, and it's also widely used in industrial. And of course, this reaction actually takes place in gas phase. So it doesn't need stirrer from the CSTR because gas actually can naturally diffuse itself. However, we recommend to use the packed bed reactor, which we actually inspired by the principle of boiling water reactor, which was designed by the Halder Topsoe, a Danish engineering company. So how this design works? So the design actually force the syngas to flow through catalyst filled tube, while the water acts as the cooling agent, where the water will be boiled at the reactor shell site. So the reactor actually operates at a nearly constant temperature, which actually offer a better conversion and of course efficient than the PFR that we use. So for this reactor, the operating condition is at T equal to 250 degrees Celsius and P equal to 79 bars. So as our reactor doesn't operate at constant temperature and pressure, because in real life, we cannot expect the reactor to be isothermal and isobaric. So the delta P that we assume is decreased by 100 kPa, while the temperature difference is increased by 10 degrees Celsius because the methanol synthesis actually exothermic reactions. So for the selection of the catalyst, we use either copper, zinc oxide, and aluminum oxide because this catalyst actually works well under industrial condition, which is aligned with our operating conditions. So the catalyst also has higher selectivity and high activity at relatively lower temperature, and it also offers good stability under high pressure, which we get better lifespan, which is between 2 to 5 years. So in the economic point of view, it's actually cheaper, commercially available, and of course it's actually been proven at the industrial scale.
We will now discuss the design of a separation system. So the primary objective of this session is to transform the crude output from the reactor into high purity industrial grade methanol. For this slide, the absorption-based purification system. So for point number 1, the cooling and feed preparation. The purification process begins by cooling the crude methanol to 30 degrees Celsius using heat exchanger. This temperature reduction is a critical preparation step as absorption is an exothermic process. So lowering the temperature significantly improves the equilibrium loading capacity of the absorbent before it enters the separator. For point number 2, the absorption column at the S1. The unit label at the S1 contains the fixed bed absorption column packed with zeolite 3A. The selection of zeolite 3A is based on the molecular size difference. Water molecules are small enough to be trapped in the crystalline pores, while methanol molecules are excluded. So this high selectivity ensures the production of industrial grade methanol. For point number 3, the continuous operation with two columns. To ensure continuous operation, a dual column system is utilized. While the PFD shows a single icon for simplicity, it represents a duty and standby configuration. This allows the plant to maintain a constant output of high purity methanol without stopping when a bed reaches saturation. For point number 4, regenerating the absorbent. The spent absorbent is regenerated using temperature swing adsorption. By applying heat, the trapped water is dissolved from the zeolite surface, restoring its capacity. This non-chemical method allows the absorbent to be reused for thousands of cycles, making the design both cost-effective and sustainable. For lastly, final product and fine filtration. The final stream, purified methanol, represents the polished product. An optional mechanical filtration step is included after the column to catch any fines or tiny particles of zeolite that may have eroded. This ensures the methanol meets strict industrial standards and prevents downstream contamination.
This slide shows the adsorption characteristic of the crude methanol stream and the adsorbent used. The feed contains several components, such as water, carbon dioxide, carbon monoxide, hydrogen, methane, and methanol. These components behave differently during adsorption. Water is strongly adsorbed due to its high polarity and ability to form hydrogen bonds. Carbon dioxide shows moderate adsorption, while carbon monoxide is weakly adsorbed. Hydrogen and methane are almost not adsorbed at all. Methanol is not adsorbed because of its large molecular size, which prevents it from entering the pores of the adsorbent. To achieve selective separation, different adsorbents are used. Zeolite 3A is used for water removal, zeolite 13X for carbon dioxide, and activated carbon for carbon monoxide. Overall adsorption depends on molecular size, polarity, and interaction forces. This allows water to be removed efficiently while minimizing methanol loss, resulting in high purity methanol.
Moving on to our adsorption equilibrium. For this system, we selected the Levenmuir isotope model. This is the ideal choice because water molecules form a consistent monolayer on the zeolite 3A surface. Our design calculation started with the feed stream, based on a total mole flow of 10,371.72 kmol per hour and a water mole fraction of 0.65. We calculated a water mass flow rate of 1 to 1,450.28 kg per hour, using a maximum adsorption capacity of 0.28 kg water per kilogram adsorbent. The theoretical minimum mass was determined. However, to account for practical limitation and the mass transfer zone, we assume only 60% of the bed is effectively used. This results in an actual absorbent mass requirement of 722,918.33 kg. Given a zeolite bulk density of 700 kg per meter cube, this requires a total bed volume of 1032.74 meter cube. Next, we translated that volume into physical dimensions. We determined the total liquid mass flow rate to be 237,758.72 kg per hour, which at the density of 790 kg per meter cube, give us a volumetric flow rate of 0.0836 meter cube per second. By maintaining a superficial fluid velocity of 0.001 meter per second, we calculated the following specifications. The column cross-sectional area is 83.60 meters squared. The column diameter is 10.32 meter. The bed height is 12.35 meter. And also, we also designed a mass transfer zone of 2.47 meter, which represents 20% of the total bed height, to prevent early breakthrough and ensure continuous efficiency.
This slide explains the regeneration process using temperature swing adsorption, or TSA. First is the heating phase, where the adsorbent bed is heated to around 200 to 300 degrees Celsius. This breaks the adsorption bond and releases the adsorbed water. Next is the purge phase, where a hot gas is passed through the bed to remove the desorbed impurities and clean the adsorbent. Finally, the cooling phase brings the system back to around 30 degrees Celsius, restoring the adsorption capacity and preparing it for the next cycle. The performance of TSA depends on several factors. Higher temperature improves desorption efficiency. The purge flow rate helps improve impurities effectively, and the cycle time ensures continuous operation of the system. Overall, TSA allows the adsorbent to be regenerated and reused, making the process efficient and sustainable.
Now, for conclusion, the first part, reactor system. For syngas-based methanol synthesis, we designed a plug flow reactor in PBR configuration using copper, zinc oxide, and aluminium oxide as catalysts to achieve 85% conversion at 250 to 280 Celsius and 54 to 79 bar, with a reactor volume of 26.63 meter cube. This confirms that PFR is more efficient choice over CSTR. For separation system, using zeolite 3A molecular sieve, an adsorption-based purification system was designed to achieve more than 99.5 weightage percentage of methanol purity. It requires 5,829,612 kg of adsorbent with a bed volume of 8968.63 meter cube. A column of diameter of 10.32 meter and a bed head of 107.28 meter with a dual column fixed bed configuration, and temperature swing adsorption TSA for continuous regeneration.